Hi, welcome back. So we're going to jump into example number 4. In this example 4, we have given a graph of the function, and we're not given the actual function. And the goal for this exercise is to be able to visualize the context of or the terminology that we've been using before and be able to visualize it in the graph. Of course, the strategies that we have discussed of how to find the critical numbers and how to create a test to determine when the function is increasing, decreasing, that's very important because we are not always rely on having a graph, right? All right, so let's begin. The first part of this is asking us to find to state the domain of the function. Remember the state to determine the domain of a function. Domain of a function is defined to be the values of x, the values of x, values of x, their input to the function, and then you get an output of a real number. You don't get always a real number. For example, if you look at x equals -1, and -1, the value, there's no value of the function. The value is undefined. The value is undefined at x equals um, at x equals -1. So in this case, we also assume that this is going forever. So basically, what we're saying is that what we're gonna do is, the way I'd like to see it is, if we sort of create a shadow of the graph. If you think about it, if we can project, the keyword is project, right? If you can project this graph, right, into this number line right here, into this number line, then that, and you can kind of figure out what is being covered. So let's try that. Let's see if we can make sense of that. So if we can project this graph into this number line, we'll see that it's actually being projected every single point in here, every point in here, every point in there, and then up to here, right? Up to here. Then here, you end up getting like a hole, right? Like a dot. Like there's no value on the function there, and then it sort of jumps, and then because of this part of the graph, then you're starting to project the graph again, right? Right here. So and then if you think about this part of the graph is projected here, so that would be this part right there. And then if you think about it, that if this part of the graph is being projected here, right? So that would be this part. It would be this part right here. So we see that the graph is projecting to this x domain, x value, everywhere except at x equals -1. So the domain of this will be -infinity to -1, open interval, and then from -1 to positive infinity, open interval. This tells us that that domain exists between those intervals, right? And of course, at the end, we always want to unite these intervals with a symbol of union. In this case, when we talk about the function being continuous, remember we talked about the function being continuous and there's no jumps, right? In this case, there is a jump, and it happens at -1. So what we're saying here is that it's going to be continuous everywhere except at -1. So it actually is even the same interval. So we're gonna have that same the same interval. Then we're gonna find where the function is differentiable, and this is going to be a little more tricky because it is differentiable everywhere, almost everywhere in here, except in two places, here and here, right? So here and here. The reason why it's not differentiable here is because there's a corner. So corners are one of the reasons why a function is not continuous, but also if the function is not continuous, right? If the function is not continuous, then also is not differentiable. So, so that means that the function is so x is differential everywhere. So it's differentiable everywhere. It will be from negative infinity all the way to this value, which is -1, -2, -3, -4, -5. So -5, and then it jumps from -5 to -1, and then from -1 to positive infinity. Right. So it is differentiable between those intervals. All right, and the next one is going to ask us to find the values where f may have a vertical tangent line. Vertical tangent line, remember the horizontal line is this one. And the way I like to think about horizontal is just like the horizon. I imagine myself looking at the ocean, or looking at the sunset, and I see the sun, right? I see the sun. So I see the horizon, right? So I see as a horizontal line. So that means the vertical line needs to be this one right here, right? This one is the vertical line. So in this case, do we see a vertical line happening? And I'm seeing here that is hard to see that whether a vertical line is actually happening, but it's actually happening here. There's a vertical line here. If you put a tangent line here, you're gonna have a tangent line that is vertical, right? So at that point, there's a vertical line. So where does that happen? That happens at x equals positive 3, right? So at x equals 3, we have a vertical line, right? And vertical tangent line, right? Let's try the next one. Let's see when what x values where the function is horizontal. So that one is actually much easy to see, right? We already talked about that it's gonna be a tangent line that is horizontal, right? So if you put a point in here, right, the tangent line for that will be a horizontal line. This one you cannot, because this is a dot, a corner. This could have many options of a tangent line, so that's why it's not that case there. So it's only happening at one place, at x equals, right, x equals 1. So that would be x equals 1. And then f is asking us to determine where the function is increasing. In other words, where the derivative is positive. So we can see here that that's going to happen not here, right? Not here, because that was decreasing, but here is increasing. So from -5 to -1, the function is increasing. So let's say that's from -5 to -1. And then also, or we can say that also from here, it seems like it's always increasing. So from +1 to infinity, right? From values of x equals 1 to positive infinity, the function is also increasing. And then we're going to unite those intervals. And then with the same argument, we can say when is the function decreasing, and that's going to happen when the derivative is negative. That is going to happen coming from here. It's assuming it's coming from the left side. It's going to be from negative infinity all the way to here, right, which is -5. And then if we notice, it's also decreasing from here to here, right, from -1 to +1. So from negative infinity, we said from negative infinity to -5, and from and then from -1 to +1. And then we unite both of them, right? And then we're going to find where the function is constant, right? Where f is constant. So this will only happen at one single moment, and that is this moment right here, right? So that, because that's where you have a horizontal line, right? So that's constant. And for that single moment at x equals 1, that function will be constant. And then now we're going to determine when the function is positive. So the function, so this is different, right? Because now we're looking when the function is positive. Well, we see here the function is positive whenever it is above this line, right? When it's above this line, whenever it's on this side of the line. It's negative if it's on the bottom line of the x-axis, right? So we can see that it's always going to be positive from negative infinity all the way to negative 1, and then from negative 1 to 0. So actually there's a jump there, right? So we're going to say from negative infinity to negative 1, and then from negative 1 to 0. And let's see what else. And then it just goes below the x-axis between 0 and 2. But then at 2, it's now above the x-axis again. So from 2 to infinity is going to be, the function's also going to be positive. And lastly, where is the function negative? The function is negative between 0 and 2, right? Between 0 and 2. 0 and 2. And then where is the function equal to 0? Well, the function is equal to 0 at 2 moments. Here, right, where the value of the function, it crosses the x-axis, and here, right, so x equals 0 and x equals 2. So x equals 0, x equals 2, right? And there you go, right? We have discussed a lot of the behavior of the function in this picture.